Welcome. In this presentation, let us visualize integration. Integration can be visualized as the cumulative addition or removal of a variable to obtain the integration function. Here, through Riemann rectangular integration strips, numerical integration is visualized. Integration should not be picturized as the calculation of area under the curve. Calculation of area under the curve is a particular case of integration. Visualize integration as a cumulative addition or removal of a variable to get the integration function. For example, tank fee. Using Taylor series, you can write y of n plus 1 is equal to y of n plus delta 1. So y of n plus 1 is the next value. For calculating that, we require y of n plus incremental value. So incremental value it is given by the product of dy by dx equal delta x, where dy by dx is the rate of accumulation. Thus, the incremental addition is the product of rate of accumulation and interval size. For example, in a flow problem, it is the product of flow rate and the interval size per step. Successive removal of a storage is a negative integration. For example, tank empty. In this case, the delta y is subtracted from the previous one. For example, if you want to calculate y of n plus 1, is y of n present value minus delta y. Here also, delta y is given by the product of dy by dx and the delta x. So let us now try to understand how integration is a cumulative accumulation. So now we have seen that using Taylor series you can find the value of the next extension. So this is the value of the next extension, and this is the value of the present extension, and this portion is the cumulative addition. So here, for example, so this is y of n, and this value is y of n plus 1. So how it is calculated? Y of n plus 1, how it is calculated? That is initial value plus dy by dx equal to delta x. So that we have seen that dy by dx is the rate of accumulation. This is the rate of accumulation. That only decides how fast the accumulation is taking place. So if you are going to the next texture, so here you can see that even at the time you can see that the accumulation is taking place. Here this will become y, this will become y plus 1. Okay. So next this is y, this is y plus 1. I think now it's clear. Okay. So how we are calculating the values by cumulative accumulation. Okay. So similarly, we can carry out the similar accumulation process in a linear rate of flow. Next, we can calculate the linear accumulation in the problems with the linear rate of flow. So the linear rate of flow, also we can calculate what is y of n plus 1. Y of n plus 1 is y of n plus dy by dx into delta x. So here, we see that this function is y of n plus 1. This point is y of n. So similarly, keep calculating what is y of n plus 1 with yn present value. So that is how we will be calculating the next value, the present value, which will give to the cumulative. So this given by this. Next, we are going to calculate the cumulative accumulation of the flow. So how the cumulative accumulation of the variable will take place. So the cumulative accumulation of the variable is given by y. So it is given by y, and the initial value is given by y naught. So y naught is 0 as per the formula we have taken for calculation of Riemann integration. So we have chosen the left Riemann integration. So that is how y naught becomes 0. Next we can calculate what will be the y1 value. So y1 value is given by y naught plus dy by dx into delta x. So in that dy by dx is the rate of accumulation. Similarly, we can calculate what is y2. So y2 is given by y1 plus dy by dx into delta x. And on the same way, we can calculate what is y3, what is y4, what is y5, what is y6, y7, y8, and the y. So here we can see that we are calculating the integration function by cumulative accumulation of the variable, which is given by dy. Next we will consider the cumulative accumulation of the variable considered in this problem. The variable considered in this problem is volume. So this volume accumulation. So here in the tank, cumulative accumulation of volume is taking place. So volume is given in this axis, and time in minute is given in the x-axis, and the cumulative accumulation it is based on the rate of accumulation. Rate of accumulation is given by volume per minute. In other words, it is in liters per minute. So here volume is given in liters, or it can be in minute also. So in this problem we are considering liters. So here the value of the volume at n plus 1 is the value of volume at n plus delta q. So that is how we have calculated. Delta q, already we have seen that it is the product of dq by dt and delta t, where dq by dt is the rate of accumulation of the volume. So now we will go by each division, for which we can calculate the cumulative accumulation of the volume. So let us consider the first division is q0. So q0 is 0 as per the Riemann formula we have assumed for this calculation. We have assumed the left Riemann calculation or upper Riemann calculation. So accordingly q0 is 0. So next value it is given by q1 is equal to q0 into dq by dt into delta t. So q1 is q0 plus dq by dt into delta t. So next q2. So q2 is given by q1 plus dq by dt into delta t. So similarly q3 is given by q2 plus dq by dt into delta t. So q4 in the same way we can calculate all the other values. q5 same formula, and then q6 is given by q5 plus dq by dt into delta t, and the q7 again same type of formula. q8 it is q7 plus dq by dt into delta t. Next q9 is q8 plus dq by dt into delta t. So in this we are finding that the integration function, that is volume cumulative accumulation,